Module 2, Atomic Structure. In material science, we want to understand materials on different scales, the largest being macrostructure, which is about a millimeter scale. When we look at these three different types of turbine blades, we can visually see that the surface of them is quite different. This level of observation would be macrostructure. The microstructure would require the use of a microscope, an optical microscope, to observe features on the micrometer scale. We can see there are differences in the grain structure shown by the inset circles. On a smaller scale than that, we can look at the atomic organization. This is how the atoms are stacked up in the material. And here we just have a graphic showing the crystal structure of the material inside a crystal of the turbine blade material. Then we can go one step smaller to the angstrom scale, where we look inside the atom and look at the structure of that. An earlier model of the atom, which is still useful, is the Bohr atom. In the Bohr atom, we have a positively charged nucleus, which is very small compared to the overall diameter of the atom. Around the positively charged nucleus, we have electrons. The charge of the electrons is equal and opposite to the charge on the nucleus to result in a neutral atom. The electrons are bound in orbits, and these orbits have different energy levels. The energy levels increase as we go away from the center of the atom. The outer electrons determine the chemical characteristics of the element, as it's the outer electrons that participate in bonding. Inside the nucleus, we have protons and neutrons. Neutrons have a zero charge, and only the protons have charge. The atomic number gives us the number of protons in the nucleus, and the number of protons will equal the number of electrons that surround the nucleus in the atom. The mass number gives the total number of neutrons and protons. It is possible for elements to have the same atomic number, but different number of neutrons and hence different mass number. In this situation, we have what we call isotopes of an element. Shown here is carbon-12 and carbon-14. And they exist with different, what are called abundances in nature. In chemistry, 1 mole of particle is roughly equal to 6 times 10 to the 23 particles. The atomic mass unit is such that 1 gram of either protons or neutrons is equal to the mass of 1 mole of those particles. In this problem, we will determine the average atomic weight of an element. Silicon has 3 naturally occurring isotopes, 92.23 of silicon-28 with an atomic weight of 27.9769 AMU atomic mass units, 4.6% of silicon-29, and 3.09% of silicon-30. On the basis of this data, confirm that the average atomic weight of silicon is 28.0854. In order to solve this problem, we're going to create a weighted sum. So let's make a table of the relative atomic mass, which is given by the symbol AR, and with a degree symbol and with the element in the bracket. So that's the relative atomic mass of silicon. And here we can put the abundance. I'll give that the symbol F. I want to now multiply those two quantities, and I'm going to add them to give a weighted sum. So let's do this. So we have, in the first one, we have 27.9769, and that has an abundance of 92.23. Silicon 29 has a mass of 28.9765 with an abundance of 4.68. And then finally, we have silicon 30 with an atomic weight of 29.9738 with an abundance of 3.09. The next steps are to multiply these two columns to create a third column. What I've done here is multiply these two columns to give, or on each row, multiply the values in these two columns to give this number here. And I've tabulated these. Next thing I've done is I've summed the abundance column. This adds up to 100%. And here I've summed these weighted quantities to calculate the average atomic weight. We simply take this weighted sum here, divide by the total of the abundance column, and this will give us 280.85 atomic mass units. In the early 20th century, quantum mechanics was developed. Quantum mechanics tells us that on small scales, matter behaves as waves and has no exactly defined location or motion. We can only calculate probability density functions of where the particle is located. We can apply the theory to atoms by solving Schrodinger's equation for the potential well created by the electric fields around the nucleus. And this predicts that, indeed, there are only certain configurations in which the electron is stable. These orbits, or stable orbits, are defined by four numbers. The principal quantum number, or the shell number, is an integer going from 1 and can increase to infinity theoretically. Within each principal shell number, we have subshells. We have an azimuthal quantum number, which is given in the letter L, and that can go from 0 to n-1, and this determines the shape of the probability density function. Within each combination of n and L, we have a magnetic quantum number, which can range from -L to +L, and this gives us the orientation. Finally, each electron can have a spin. It can be a positive or negative. At this link, if you follow this link, the probability density functions for different orbits are visualized. In the ground state of an atom, we're looking at the state in which the electrons have the lowest energy states possible. Key to determining this is called the Pauli exclusion principle, which states that each quantum state, in other words, each combination of these four numbers, can only accommodate one electrons. or in other words, no two electrons can have the same quantum state. Again, there's no option there, but the spin quantum number can be plus or minus half, and this means that we can accommodate two electrons in the n equals 1 shell. In the n equals 2 shell, L can go from 0 to 1. When L is 0, M can range from 0 to 0. And within each combination here of n equals 2, L equals 0, M equals 0, we can have spins of plus or minus half, and that allows us, once again, two electrons in this shell right here, which is known as the S shell. When L equals 1, known as the P shell, we can have the magnetic quantum number go from -1, 0 to 1, and each of those accommodating two electrons. So we can accommodate 6 in that P subshell. This gives us a total of 8 electrons that can be accommodated in the n equals 2 shell. With n equals 3, L can range from 0, 1 to 2. When L equals 2, that is called a D shell. S, P, and D are names that come from spectroscopy. Within the L equals 2 shell, the M number, the magnetic quantum number, can range from -2 to -1, 0, 1, and 2. Each of those accommodating two electrons, which gives a total of 10 electrons in the D subshell. When we add these up, we can see that the n equals 3 shell can accommodate a maximum number of 18 electrons. When the atom is within its ground state, it will have the lowest energy. The electrons will fill these shells in order of lowest energy first. A more accurate model, which includes relativistic effects, will allow us to see how the energies of these different subshells compare. Initially, we can see that the energy correlates with the principal quantum number, which it generally does. We can see that the S shell has the lowest energy, and then P, and that's a trend that occurs until we get n equals 3. Here you can see that the 4S shell actually has a lower energy than the 3D shell. This is neatly summarized in an outby diagram for the shell filling order. We can use this diagram to determine the ground state configurations. For example, let's look at argon. Argon has an atomic number of 18. So how can we put 18 electrons into the ground state? So we start here. We can see that we have the 1s shell, which we know can accommodate only 2 electrons. Then the 2s, which again accommodates only 2 electrons. The 2p, when it's filled, accommodates 6 electrons. Next to fill is the 3s, which accommodates another 2. And then we have the 3p, which accommodates 6 electrons. The electron shells and subshells are fully filled in these noble gases. Now let's look at iron. Iron follows a similar pattern as argon, up to 18. But for the remaining 8 electrons, so we have 3s, here we go. So the next to fill up after that, surely, is the 3p6, sorry, that's the same as argon. And then after that, we've got 4s2 filling up. And instead of the p, what fills up next is the 3d. Okay, up to the 3d only has the remaining 6 electrons. Remember, a fully filled D shell can accommodate 10 electrons, so we see that the 3d shell is only partially filled. we can more easily rewrite this configuration using a noble gas as a root here, and then just adding on the additional electrons and their configuration. In an atom, the valence electrons are those electrons that are in the energy band with the highest shell number. The chemical characteristics of an atom are principally determined by the outer electrons, as they determine how the element will combine with other elements. In the periodic table, elements are arranged into columns, with each column having elements with a similar valence electron configuration, and hence having similar chemical properties. An important concept is electronegativity, which is a term developed by Linus Pauling. It relates to the tendency of an atom to accept electrons. Let's take the example of sodium and fluorine. Sodium, with an atomic number 11, has an electronic structure with filled shells up to 2p, but then an unfilled shell, 3s, with only a single electron in the 3s shell. This atom would be stabilized to form an ion by losing this electron, or become further stable by losing this electron to form an ion. Similarly, in the fluorine atom, which has an atomic number of 9, its valence electrons are such that in the 2p subshell it is almost filled and is missing one electron to be completely filled. This atom would be stabilized by accepting an electron to form a negative ion. So when we bring sodium and fluorine together, we will have an exceptionally violent reaction where the sodium will lose an electron for it to be gained by the fluorine the fluorine atom. Fluorine is the most electronegative element and has a electronegativity of 4, or around 4. Inert elements, or noble gases, have completely filled subshells, and so what this means is that it is difficult for it to bond with other atoms. The electronegativity values on the Pauling scale are shown in this diagram. We can see fluorine being the most electronegative. At the other end of the scale, we have low electronegativity numbers by elements in the first group. Bonding between atoms can be classified into 4 main types. An understanding of the type of bonding between the elements in a material can allow us to predict some of the properties of that material. The key types of interatomic bonding are ionic, covalent, metallic, and van der Waals. With ionic bonds, which occur when an electropositive atom binds with an electronegative one, in other words, one atom will donate an electron and for it to be accepted by the other atom, thus forming oppositely charged ions. Such oppositely charged ions can form bonds, and these are called ionic bonds. In such a structure, the movement of ions can result in some electrical conductivity, and it tends to result in a very stiff crystal structure, because although the bonds are not directional, in order to slide one plane of atoms across another will mean forcing 2 equally charged ions to be close to each other. So this explains why ionic materials tend to be hard and brittle. Covalent bonds are formed by sharing electrons to form a stable relationship. Such bonds have a fixed directional relationship, and this can result in a stiffness in the material. The electrons are fully localized and not free to conduct electricity. In a metallic bond, again, the bond is created through sharing electrons, but due to the periodic nature of the crystal, some of the electrons are able to move around the crystal and such contribute to electrical and thermal conductivity. The bonds are not directional, which allows planes of atoms to slide with respect to one another, which results in a ductile material. Van der Waals forces are weak forces due to the interaction of molecules that have become polarized. A common form of this is called hydrogen bonding between water molecules. It is this hydrogen bonding which is responsible for the formation of crystals of ice, which ice has a more open structure and is less dense than water as a result. Although we have categorized those four types of bondings, in many materials the bonding is a mixture of two or more of those principal types. For instance, many metals have a mixture of metallic and covalent bonding, which can give rise to directional bonds that force the material to adopt a lower packing density, such as with iron. In ceramic and semiconductor materials, we can have a mixture of covalent and ionic bonding. The greater the electronegativity between the atoms, the more ionic in nature becomes that bond. And the fraction of that bonding that is covalent can be estimated from the following equation as proposed by Linus Pauling. So the covalent fraction, which is a number from 0 to 1, is equal to E and to the minus 0.25 times delta E here. And delta uppercase E is the difference, the size of the difference in the electronegativity between the elements. Note that thus delta E is always positive number in this equation. For example, let's compute the percentage ionic character of the interatomic bonds for each of the following. With MgO, we are looking for the percentage ionic character. Notice that that is equal to 1 minus the percentage covalent character. And hence is equal to 1 minus e to the minus 0.25 times delta E squared. Let's have a look at the electronegativities for magnesium and oxygen. Magnesium has electronegativity of 1.2, whereas oxygen has electronegativity of 3.5. Delta E is going to be the size of that difference. Which is equal to 2.3. So therefore, the percentage ionic character is, sorry about that, let me just write that better. 1 minus e to the minus 0.25 times 2.3 squared. When we calculate this, we get a fraction of 0.733, which expresses the percentage is 73%. So we can see that magnesium oxide is characterized as an ionic material or ionic crystal. The binding energy is the energy required to break apart a bond. And here we see it listed in units of kilocalories per mole. We can see that the van der Waals bonding is very weak, and it doesn't take much energy to break them apart. Metallic bonds are the lower part of it is in the lower range, although the upper part is overlaps with that of covalent and ionic solids. The covalent ionic solids tend to have larger binding energies for their bonds. In this problem, we are asked to make a plot of bonding energy versus melting temperature. And when we do that, we see there is a correlation between melting temperature and bonding energy. Higher temperatures are required to melt materials with higher bonding energy. We can see that those materials here with the highest melting temperatures include, we've got carbon, diamond in the form of diamond, tungsten, and magnesium oxide. Carbon in the form of diamond has covalent bonds. Tungsten has a metallic bond, and magnesium oxide has ionic bonds. So you can see it's not completely predictable just from knowing the type of bonding and what the melting temperature will be, whether it will be high or low. But generally speaking, we do expect that materials with covalent and ionic bonds will have better high temperature resistance than metallic, and certainly more than van der Waals materials or materials that rely on van der Waals forces for bonding.